Hi guys, how's it going? So today is the last session and we are going to just solve a few additional examples about influence line analysis, and you're going to see how to use this method for finding the maximum force or bending moment in structures. So last time we could reach this slide, which is about the very important application of influence line analysis and influence line diagrams in structural analysis. By now, we know how to use Muller Breslau's method for drawing influence lines. And now in this example, you're going to see how to use these principles and these diagrams for understanding the maximum demand that can be created in a structure due to live loads or due to some loads that can be changed during the life of the structure. So far, before this chapter, I mean in chapters 1 to chapter 4, we discussed the loads that were constant and they did not experience any change during the time. So we could analyze the structure under the load and we could understand what is the maximum force in different members. And then based on that maximum force, we could design the member. Of course, we are not going to design that in this specific course, but later in your design courses like concrete design or steel design or bridge engineering, based on that maximum force, you will design the sections or the structure. The question that we tried to answer in this section or in this chapter was about the live loads, the loads that can be moved along the structure over time. How should I understand the maximum force that can be generated in one member or in the structure according to a load that is being changed or moved during the life of the structure? We use the concept of influence line for answering that question, and over here you can see how we are going to practically discuss that question and answer it in one example. So you can see this beam is given to us. It is asking us for finding the maximum positive moment that can be developed at point D, this point over here. If a concentrated moving load is applied to the structure or to the beam, a concentrated moving load of 4,000 pounds, that's one case. Another case is a uniform moving load of 300 pounds per foot. Since these are moving loads, we can say all of these are kind of live loads because these are changing over time or during the application of the structure. And at the end, it is asking about a case of beam weight of 200 pounds per foot. So the question is asking about the maximum moment that can be created at D according to these cases. The first case is talking about a concentrated moving load of 4,000 pounds. The first question is, where should I put this concentrated moving load to get the maximum bending moment at D? That is the question. And for answering that, we need to draw the influence line for bending moment at D. How can I draw the influence line? We can quickly use Muller Breslau's principle for that. Based on that rule, I need to remove the restriction for that specific force or moment and then apply a uniform deformation and see the deformed shape of the structure. Once you do that, the deformed shape will be the influence line diagram. Over here, we are talking about bending moment at D. So I said when we are removing the moment restriction, it means that we can simply apply rotational deformation at that point. In other terms, we can assume there is a hinge over there. By removing the rotational or moment restriction, it's like applying a hinge at that specific point. Then we can pull that hinge, we can grab that hinge and pull it up. The deformed shape that you see on the structure is the influence line, is the bending moment influence line for that point. So I'm going to consider a hinge, moving it up, and then I'm going to see a kind of mountain shape over here. At point C, we have to have the deflected shape at this specific point because we have a support over here. So this specific point is not going to experience any displacement. So it goes up over here, then it goes down. Over here we have a hinge and also a hinge over here, so it can simply be rotated. If I draw that, we will see a situation like this, right? This is this dashed line is the deflected shape, and this is the influence line diagram for bending moment at point D. We could understand the configuration, and the question is now, what are the values inside this diagram, or this H and H prime? For that, the important information that I need to use is the fact that this angle over here is 1, theta is equal to 1, because we said for using Muller Breslau's principle, I have to remove that specific restriction and then apply a unit deformation. In the case of shear force, that means a unit displacement. In the case of moment or bending moment influence line, I have to remove the rotational restriction and apply a unit rotation. That's why this theta over here is equal to 1. Based on our geometrical knowledge, we know this exterior angle, or this theta, is actually the summation of theta 1, or this angle 1 over here and this angle 2 over there. So theta 1 plus theta 2 is equal to 1. And since these are small angles, I know theta 1 is equal to h over 10, and theta 2 is equal to h over 5, right? I'm looking at these two triangles. So summation of the angles are equal to 1. Putting these ratios instead of the angles, we can see h is equal to 10 over 3. I could find h. Now I can look at these two similar triangles over here, this one and this one. And by comparing those, we can see these are similar triangles, and we can write the ratios for these similar triangles like the procedure that we did for several previous examples. H over 5 is equal to h prime over pi, h prime over 5, and having these ratios over here, we can find h prime as 5. Now we could understand the values inside the influence line diagram. So based on this diagram, now the question is, what is the maximum positive bending moment that can be created at point D based on a concentrated moving load of 4,000 pounds? In other terms, where should I put this concentrated moving load to get the maximum bending moment, maximum positive bending moment at point D? Based on this diagram, if I put it over here, right at the top of this mountain, right over here, or we can say right at the location of point D, I'm going to get the maximum positive bending moment. If I, for example, wanted to know where should I put it to get the maximum negative bending moment, I would say I have to put it over here, right at 5 feet from point A, to get the maximum negative bending moment at point D. So based on this diagram, we could understand that if I put that 4,000 concentrated load right at this location, 15 feet from point A, or right at point D over here, I'm going to get the maximum positive bending moment at point D. What is the value of that bending moment? I have to multiply the amount of load, which is 4,000, by the height of diagram, which is h over here, and that is 10 over 3. So 4,000 multiplied by 10 over 3, and pay attention to the changes in the unit because that was 4,000 pounds, all the values that I have in my influence line diagram are kip foot per kip. So this pound should be changed to kip, and once I do that, you can see the maximum positive bending moment that can be created at point D due to a moving load, a concentrated moving load of 4,000 pounds is equal to 13.33 kip foot. That's how we could understand the maximum influence of a moving load or live load on the structure. And now I can design this beam based on this maximum influence that it can get from this moving load. So that was the first part of this question. The second part is asking about a uniform moving load of 300 pounds per foot. So instead of a concentrated load, now we are looking at a uniform load. How should I place or put this uniform load on the beam to get the maximum bending moment at point D? Again, I have to look at the influence line. I can see these are the regions that we get maximum, these are the regions that we get positive bending moment at point D. These regions that we have positive values in the influence diagram. So I'm going to put this uniform load or kind of distribute it or distribute this uniform load in the positive region of the influence diagram. Over here you can see the positive region, so I'm going to put the uniform load over here, and now I can understand the maximum positive bending moment that can be created at point D because of this moving uniform load. We are calling this a moving uniform load because the load can be changed during the life of the structure. It might be at some location at some time, and at another time it might be at another location. That's why we distributed like this, and we had the ability to distribute it because the question said it is a changing or it is a uniform moving live load of this much. So since it is moving, we can just distribute it in specific regions that we want. In this specific question, I wanted to know the maximum positive bending moment at D, so I distributed this uniform load over here in the region where we have the positive values in the influence diagram. So what is the value of the moment? I have to multiply the intensity of that uniform load by the area that I have inside the diagram. That will give me the moment because of this moving load, because of this uniform moving load at point D. That's what I did over here. 300 pound-feet is the intensity of the uniform load. I have the change of units over here because the influence line diagram is based on kip foot per kip. So this pound per foot should be changed to kip per foot. That's the change over here, and then I multiplied it by the area of this diagram in the positive region. 10 over 3 multiplied by 15 divided by 2. That's the area under this triangle. Once you calculate this, you can see the maximum moment that can be created at point D because of this uniform load is equal to 7.5 kip foot. That was the second question, or the second case in this question. The third case is asking about beam weight of 200 pounds per foot. Again, we have a uniform load, but the important difference is the nature of the loads. At part B or case B, we talked about a uniform moving load, which was a live load. In case C, we are talking about beam weight, which is dead load. When we are talking about dead load, it means that we don't have the freedom to distribute it in different regions. It is always distributed in the whole length of the beam because it is weight of the beam. It is always there. As long as we have the beam there, the weight is over there and it is being applied to the beam. So for that, all I can do is to just consider the beam weight in the whole length. Again, since it is a dead load, I don't have the option of distributing it in a specific regions. It is always over there during the whole length of the beam. Now, based on this distributed load, what is the maximum moment that can be created at D? That is just calculating the area that we have under the diagram multiplied by the intensity of uniform load. To be more accurate, I have to say what is the positive moment that can be created at point D, or what is the moment that can be created at D, because saying maximum positive or maximum negative does not have any meaning in the case of dead loads, because dead loads are always over there, they are not going to change. I cannot say, for example, I'm going to put this dead load over here or over there to get the maximum negative or positive. It's always there. So saying maximum positive or negative is meaningless. When we are considering a dead load, we can just say what is the bending moment at point D because of this dead load, because of this dead load or self-weight of the beam. And that is the case that we were discussing and learning from chapters 1 to chapter 4. From chapter 1 to chapter 4. But in the very last chapter, which is this one over here, we talked about live loads, and in the previous cases, we could see how we should deal with them and find the maximum bending moment or force based on that. So I have the dead load distributed like this, and now all I need to do is to see what is the moment at D. I have to multiply the intensity of the load by the areas that I have under the diagram. Over here I have a negative area, and over here I have a positive area. That's why in the positive region I have this term, and in the negative region I have this term. I'm just multiplying the intensity of the load by the area under the diagram. Once you do that, you can see the the moment that can be created because of this dead load at point D is equal to 1.67. Again, saying maximum positive or maximum negative does not really have any meaning in case of considering dead loads, because we cannot play with them. It's just over there, and we have to just calculate the moment because of that dead load. Ultimately, we can say, or we can consider an additional situation, which is what is the maximum bending moment, or what is the maximum positive bending moment that can be created at point D because of all of these loads, because of a moving load of a concentrated moving load of 4,000 pounds, a uniform moving load of 300 pounds per foot, and dead load of the beam as 200 pounds per foot. In that case, dead load is over there during the whole length. I can't put the uniform load, live load, in the region where we have the positive bending, and I can't put the moving concentrated load at exactly the place where it creates the maximum positive moment. Considering all of these, I can calculate the maximum positive bending moment that can be created at point D because of all of these loads. Since I already calculated each of these separately, I just added them together. But if you were to look at this as just a question with this situation, let's say we had this question, and instead of having 3 cases, it could say find the maximum positive bending moment at point D when a concentrated moving load of 4,000 pounds and a uniform moving load of 300 pounds per foot, and also the beam weight of 200 pounds per foot is applied to the beam. In that case, I have to consider this situation and then multiply the intensity of uniform loads by the areas under the diagram, and multiply this concentrated load by the height of the diagram at this specific point. If you do that, you can see the maximum positive bending moment at point D because of all of these loads together will be equal to 22.5 kb foot. I believe it is the most important example in this chapter because it shows how we can use the influence line diagram in terms of analyzing a structure, and it shows the ultimate application of influence diagram in finding the maximum demand in a structure or at a specific point in a beam under a live load, and we can design that member based on that result that we get from the influence line. So it was the last example in the presentation file, and after this I'm going to look at a few examples in a separate file which I posted on Canvas. So over here we have a few examples to solve. I believe by solving these you will be pretty much familiar with the procedure of drawing influence lines, and also the way we can use them for finding the maximum demand on structures according to live load. The first example is about drawing influence line for vertical reaction at A, shear at C, and moment at C. So I said, based on Muller Breslau's method or principle, I have to remove the restriction for that specific force or moment and then apply a unit deformation. For the case of shear force, that unit deformation is unit displacement. For the case of bending moment, that unit deformation is a unit rotation. And then once you do that, the deflected shape is your influence line diagram. The thing that you have to have in mind is that the restriction that you are removing for the structure for applying the deflection is just for that specific moment or shear in that point. You have to keep the other restrictions in the structure as they are, and you cannot change them. That's how you can draw the deflected shape correctly and obtain the influence diagram for that specific force or moment. Over here, the first part of the question is asking about reaction at A, vertical reaction at A, as you can see in this portion of the question. So for that, I have to remove the vertical force or the restriction for vertical force at A and apply a unit displacement. That's what we have over here, right? We have a roller support over here, and the beam cannot experience any deflection. Any displacement. That's why at the end, the deflected shape is returning to point B as it is in the undeformed shape. But since it's a roller support, it can experience rotation, and that's why we could apply the unit displacement and see such a deflected shape for the beam. Right? So that was the vertical reaction at A. And the values are not difficult to find. We said it's a unit displacement, so this is just one, and the unit is just kip per kip. Of course, that is for the case of having American units, but in this specific example, we are not showing any values or any dimensions, so that's why I didn't include the units for the influence line. The second part of the question is asking about shear force at C. So when we want to draw the shear force influence line, I have to remove the shear restriction, which means we can apply a unit displacement. But the thing is that the two segments of the beam should be parallel to each other, because the thing that we removed from the structure is the shear restriction. The moment restriction is yet over there, which means that we cannot have rotation in the two segments of the beam. We just consider two segments at point C, this point, and then I applied a unit displacement. Once you do that, you can see a situation like this. I know I'm going to have two portions or two parts, A and B, as the length of these kind of segments of the displacement. I know the total displacement that I applied is equal to 1, so A plus B is equal to 1. And the other information that I know is that these lines are parallel. or in other terms, these angles are equal. So B over AC is equal to A over CB. And based on these two equations, I can find the values of A and B, and later we can use it in future questions. But this is the influence line for shear at C. And the last part is asking about moment at C. So now instead of removing the restriction, I'm going to remove the rotational restriction, which means I can consider a hinge at C, grab the hinge, pull it up. The deflected shape will be the influence line for moment at C. That's what we have over here. See, you consider the hinge, pulled it up, that is the deflected shape. But the thing is that sometimes based on the boundary conditions that you have, you may consider this unit rotation in other forms. But the very basic guide that I can give you to help you solve the problem is consider a hinge over there and then apply a unit rotation. In this case, we could consider a unit rotation like this. In some cases that you will see in future or in other examples, the unit rotation that I can apply might be just in one segment instead of two segments of the beam. So now that I know the configuration of the influence line, I need to find the inside the diagram, and for that I can say this exterior angle is equal to the summation of these two interior angles. That's based on our geometrical knowledge. So theta 1 plus theta 2 is equal to 1. These are small angles, so theta 1 is equal to h over AC and theta 2 is equal to h over BC. When we are talking about the small angles, tangent of the angle is very close to the angle itself. That's why we can have such ratios. Having this ratio over here, I can simply find the value of h, and once you do that, the question is solved. You have the influence line with all the details for bending moment at C. So that was the first example. In the second example, we have this situation. The question is asking about using Muller Breslau's principle for finding the influence lines for vertical reaction at A, shear at D, and bending moment at B. So the first is vertical reaction at A. It is a force, like a shear force. I have to remove the translational, or I have to remove the shear restriction. And once you do that, you can apply a unit displacement. Right? When you apply a unit displacement, it's like pushing this side up, and then the deformed shape will be the influence line for vertical reaction at A. That's what I have over here. I remove the shear restriction or vertical restriction at A, applied a unit displacement, and then the deformed shape that you will see will be the influence line for vertical reaction at A. This value over here is equal to 1 because that's based on the definition of that's based on the very basic definition of Muller Breslau's principle. You have to remove the restriction and apply a unit displacement. So this is equal to 1. This side, the value can be obtained or found by considering the ratios for these two triangles. 1 over AB is equal to A over BC, and we can find this value by considering this ratio. So that is the influence line for vertical reaction at A. Then it is asking about the influence line for shear at D. That means I have to remove the shear restriction and apply a unit displacement. Again, it is just removing the shear restriction. The moment restriction is yet over there, which means we cannot have any rotation in the two segments, which means the two lines that you get on one side of D and the other side of D should be parallel. So let's apply that unit displacement. This part goes up, this part goes down, and then the two lines are parallel. So I'm going to see those two parallel lines like this. This is the situation. At B, I have this roller support, so the beam cannot influence any displacement at B. That's why we have this shape as the influence line for shear at B. The thing that I know is that these lines are parallel, so these angles are equal. And the other thing that I know is that the displacement that I applied at D is equal to 1. So A plus B is equal to 1. These angles are equal, this angle and this angle. So B over AD is equal to A over DB. Based on this, I can find the values of A and B, and once you find that, you can look at these two similar triangles. We can say A over DB is equal to C over BC, and based on this, you can find the value of C. The last part of the question is asking about bending moment at B. I said whenever we want to draw the influence line for bending moment, we have to remove the rotational restriction. It's like considering the hinge and then apply a unit rotation. In the previous examples, I said we can grab that hinge, pull it up, and see what happens. In this case over here, we are looking at a point right above the support. And when it is on the support, excuse me, since it is located right above D, we cannot have the displacement, and that means when we consider a hinge over here, the rotation can be applied when the point is exactly at its place above the support at B. So I have to apply a unit rotation. On the left segment, it is a horizontal line because at A, it stands over here. At B, it should remain as it is because of the support. The only segment that can be rotated or can experience the deflection is segment BC. So I'm going to apply a unit rotation to this segment. That will be the influence line for bending moment at B. And as you can see, it is shown over here. Having it or having the rotation clockwise or counterclockwise is just about having positive bending or negative bending. That does not make any change in this specific case, and it's both correct. You can consider this unit rotation upward or downward. I mean clockwise or counterclockwise. But the important thing over here is just the value of this A. I know this angle is equal to 1, so A over BC is equal to 1, and you can simply find the value of A in this diagram, which is the influence line for bending moment at B. That was all the things that were asked in this question. I believe the only important over here was, or the most important part of this question was the bending moment at B, the influence line for bending moment at B, because we used to consider a hinge and then grab that hinge and pull it up. Over here, we cannot have that kind of form of deflection because the support over here, but you have to have it in mind that whenever you have the support and when you are considering the bending moment influence line or bending moment restriction, you cannot have that displacement. You have to just apply the rotation. So that's about this example, and let's move forward to the third example, which is this one over here, and it is asking about the influence lines for vertical reaction at A, shear at D, and moment at D. So it's vertical reaction at A and shear and moment at D. Vertical reaction at A is not difficult. I have to just consider the vertical force or the vertical restriction over there, remove it, and then apply a unit displacement. Once I do that, I'm going to see a shape like this. We have a hinge over here, which means this portion can experience rotation. This side of the beam is connected to this fixed end, which means we cannot have any rotation or displacement at end C. So that forces this portion to be completely horizontal as it is, and the only segment or portion of the beam that can experience deformation is segment AB. That's what we have over here. That was the reaction at A, and now he is asking about shear at D. So when we want to draw the shear influence line, I said we have to remove the shear restriction, which means we will be able to apply a unit displacement, but we have to have it in mind that the two segments should be parallel after applying the displacement, because the moment restriction is yet over there. We cannot have rotation at that specific point, which is point D in this example. It's just a shear restriction, so I have to apply a unit displacement and the two segments should be parallel, which means I have to apply the whole unit displacement on the left segment. It will be moved up. The right segment or the right section of D will be horizontal as it is because of this fixed end. We will have a unit displacement on this, and then we will have a rotation at D because of the hinge. That's what we have over here. Unit displacement. Left side of point D is parallel to right side of point D. That's because we are keeping the moment restriction as it is. We have not removed that, so the two lines, or the left side and right side, should be parallel. That's why we have such configuration. And then at B I have a hinge, so it can have rotation and it should return to its original location at point A because we have the support over there. It cannot experience any displacement. It can experience rotation because it's a roller support, and if it was a hinge support, yet it could experience rotation. But if it is fixed something like this, it would not be able to experience any rotation. So that is the influence line for shear at D. Then the question is asking about the influence line for moment at D. For that, I have to consider a hinge because rotational restriction is removed. We can consider a hinge over here, and then I have to apply a unit rotation. Since it is fixed over here, this portion cannot be displaced or rotated. This is as it is. The whole rotation should be applied to the left segment, and then you're going to see a mountain shape just at the left side of point D, and that is what we have over here. Again, having it upward or downward, that is your call. I mean, that's just considering the positive moment or negative moment. But the general configuration is like this. As you can see, we applied a unit rotation. This angle is equal to 1. And then since these two sides or these two parts are equal, we can say this one is equal to 1. And for finding the value of h, we know that theta is equal to 1. So h over bd is equal to 1. And we can find the value of h by considering this ratio. So that was the third example. Over here we have the fourth example, and it is asking about the influence line for vertical reaction at A, shear at the left side of this roller support, shear over here, and moment at A. So vertical reaction at A, moment at A, and shear right at the left support at the left side of support E. So for finding the vertical reaction at A, I have a fixed support over here. I have to just remove the shear restriction so I can apply a unit displacement. But since it is fixed, we have to maintain the moment restriction, which means we cannot have any rotation. So just a unit displacement, and it is completely horizontal because it cannot have any rotation. You can see that over here. We have a hinge over here, so it can rotate from point B to point C, another hinge at point C, so it can have the rotation like this. The reason that we had such rotations is that at points E and D, we have the roller supports, which means that the beam cannot have displacement at points E and D. So the deformed shape should return to the original location of the beam at points E and D because of those roller supports. That was the vertical reaction at A. Then we have to find or draw the influence line for shear at the left section or left part of the support. It says just to the left of the roller support E, which means shear right on the left side of E. For that, I have to consider the shear restriction or displacement restriction. I have to remove that and then apply a unit displacement. As you can see, point E is right at the location of the support. So on the right side, it cannot experience any displacement. It remains as it is. On the left side, however, it can experience the displacement. The important thing is the hinge that we have over here. This hinge will help us to maintain the restrictions that we have at point A. So a unit displacement should be applied. I know on the right side it cannot have any displacement because of the support. On the left side we are going to have the whole displacement, and then at hinge we can, at point B or hinge B, we can have the rotation. So I'm going to see a thing like this, a line like this. And then the other important thing is that we have a continuous beam over here. We just removed the shear restriction. The moment restriction is yet over there. So the lines before point E and after point E should be parallel. That's why the line that we have over here should be also seen over here at the right side of support E. And then at C we have a hinge, so we can see a mountain shape because of this hinge over here. At point D, the deflected shape should return to the original shape because we have a support over here and we cannot have any displacement. So that is the shape that we were talking about. I applied the unit displacement at the place of the location the question was asking for. The question was asking for shear at the left of point E. So I applied the unit displacement over there. Then, because we have to maintain the rotation restriction, we cannot have any rotation over here. That's why the lines are parallel right before the section and after the section. And then this is the configuration. This side is completely horizontal without any deflection because of this fixed support. We cannot have any rotation or displacement at point A. And I believe that's all the explanations that we have to have for considering the shear right at the left side of joint E or support E. It is not the influence line for reaction at E, it is the influence line for the left side of the support at E. The final thing is the moment restriction at A, or the influence line for moment at A, which means that we have to remove the rotational restriction. The displacement restriction should be there. I cannot have displacement over there. I have to just apply a unit rotation. Once you do that, we can have something like this. Because of these hinges, we can have rotations at the locations of the hinges, and we have to make sure the deflected shape returns to the original shape or to the original location at the place of these supports. That's why we have a shape over here. When you draw this, you may apply this rotation on the other side. I mean, you can have a shape like this. This positive can be negative, this negative can be positive. That's fine. The thing that matters is the general configuration. We have to have a unit rotation over here at the place of the support. That's theta equal to 1, and then H can be found by just considering the ratio of H over AB. Because theta is equal to 1, it means H over AB is equal to 1. So that was example number 4, and over here you can see the last example, which is example number 5. So this is the last example, and it is very similar to the example that we had at the end of the presentation. It is about the application of influence line analysis for finding the maximum demand in the structure because of moving loads or live loads. It is asking about the maximum positive moment at C and maximum positive shear at C based on a distributed live load of 1.5 kilonewton per meter and a single concentrated load of 8 kilonewton as the live load. These are the distributed live load of 1.5 and the concentrated load of 8 kilonewton. These are live, and it is also giving us the information about dead load, which is 2 kilonewton meter. And now it is asking about the maximum positive moment at C and maximum shear at C. So when we want to know the maximum moment, the maximum positive moment at C, all I need to do is to consider the influence line for bending moment at C, and then once I draw that, I can apply the loads to get the maximum positive bending moment. Drawing the influence line for moment at C is not difficult. I have to consider a hinge over here, apply the unit rotation, and since this point is just in the middle of the beam, we can consider a hinge and grab it, pull it up, and the deflected shape will be the influence line for bending moment at C. That's what I have over here. As you can see, this is the moment at C. This is the hinge that I considered. We applied a unit rotation, and that is the situation. Since we have a support over here, the deflected shape should be at the location of the original beam at the support. That's why we have this shape over here. So now I need to find the values inside the diagram. This H can be found based on the fact that this angle is equal to 1, which means summation of these two interior angles is equal to 1. This angle is equal to H over 2, and this angle is equal to, again, H over 2. So based on this, we can find H as 1. These are SI units, so it is kilonewton meter per kilonewton. That is the unit for bending moment influence line. And then once we have this diagram and we know the value of H, we can say the dead load is applied on the whole length. We cannot change that. The live loads, the uniform live load, can be applied over here in this segment from 2 meter to 6 meter because we have the positive moment over here. And the concentrated load should be exactly applied right at this point at 4 meter to get the maximum bending moment at point C. Once you consider that over here, you can see how I calculated the maximum positive moment at C. That was a concentrated load of 8 kilonewton, so that 8 is multiplied by H, the place where it is applied. Then we had the live load of 1.5 kilonewton per meter. I have to apply that load in the positive region, so intensity of the load multiplied by area under the positive region, which is H multiplied by 4 divided by 2, the triangle. And then we have the dead load, which is applied in the whole length, which means the intensity of the load multiplied by the area under it. We have a negative region over here, that's this portion, positive region over here, this portion. Calculate the whole thing. The maximum moment that can be generated at point C because of those loads that we talked about is equal to 13 kilonewton meter. The other part was asking about maximum shear at C. For considering the maximum shear at C, I have to consider the shear restriction, remove it, apply a unit displacement, and after that I have to just draw the deflected shape. That is shown over here. I know B plus A is equal to 1, and I know these lines are parallel because we just removed the displacement restriction. The rotational restriction is over there. That's why these lines are parallel and these angles are equal. So A over 2 is equal to B over 2, and based on this we can find the values of A and B, and you can see both of them are equal to half. Now that we know A and B, based on similar triangles, I can find the value of C, and since these are equal segments, C is also equal to 0.5. So we know the influence line for shear at C, and now all I need to do is to apply the loads in the proper locations to get the maximum positive shear at C. I want the maximum positive shear, so the uniform live load should be only applied in the positive regions. The concentrated moving load should be only applied at this place to get the maximum influence of it as the shear at point C. Excuse me. And the dead load is applied in the whole length, and we cannot change that. That's just the dead load, and it is always over there. So 8 multiplied by 0.5, that's because that load is applied right here. Then I have the live load that is applied over here from 4 to 6, and also over here from 0 to 2. That is the influence of that, and then the dead load in the whole region. That is the calculation for that. You can see the maximum positive shear at point C based on this loading will be equal to 6.5 kilonewton. I believe it is pretty straightforward. Once you draw the influence line, you have to just apply the loads in a way that they create the maximum force or moment in that specific point. That was the last example. If you have any question, if there is anything that we need to discuss, don't hesitate to send me an email. We can schedule a time for meeting and discuss that. And I really appreciate your patience. I know following these in the online course and in these recording files was not easy, but I really appreciate your patience. I really appreciate your understanding. And thanks a lot. Take care. And I hope to get the best grade in the final exam. Don't worry about your grade and just do your best. Thank you. Bye.